Alright everybody, I'm going to show you how to use Microsoft Excel to determine the order of a reaction based on the integrated rate law. But first, I wanted to capture this moment in history. We had a cold day today, January 7, 2015, because the weather was so cold. And tomorrow, Thursday, it is quote-unquote much warmer than today, and it's going to snow 1 to 3 inches, and so therefore we have school tomorrow, but it's still going to be pretty nasty. Look at this, winds could occasionally gust over 40 miles per hour, and if you look at the time data, around 7 a.m., which is when I'm going to be dropping my son off at school, even though the temperature is only -8, it's going to feel like -28 because of that 13 mile per hour wind. And when you all get to school, which will probably be around 8:30 or so, oops, what happened to my data table here? Which will be around 8:30, it's going to be not much warmer, about -28 degrees. Phew! And when you get home, it'll feel like it's -12. If you look at the wind chill chart at a temperature of, excuse me, -8 with 15 mile per hour winds, we still could have frostbite in 15 minutes or less, so stay warm. Alright, looking back at our data, this is the data from AP worksheet from Adrian Dingle's site, worksheet 04B. This is question 3, and I've already populated in that data of time versus substance A. And we know that substance A has to be a reactant because it's being used up, because the concentration is decreasing over time. How would you measure the decreasing concentration over time? You would probably use spectrophotometry to see the disappearance of that color. That would be one way you can measure that. Okay, so I'm going to go to View, Normal to get rid of that page break. I'm going to go to View, Elements Gallery, and I am going to click on Charts. I'm going to select and highlight my XY data. I like putting them in XY. I'm going to click on this one. You can connect the dots if you want to. There's my general graph. So we can see that it is not zero order because it's curving down. Some of you might automatically say that it's first order, but it may not be first order. It could be second order, because a second order graph would look like this. It would be a steeper decay, but I can't tell visually if it's first order or second order by looking at the decay graph. So we need to make a graph of the natural log of the concentration of A. And I'm going to make, excuse me, I have a little cold here. All right, now I'm going to have Excel calculate those values for me. I'm going to say equals ln, and notice it becomes a function, and you can select that function, and it tells you have to put something in those parentheses, and I'm going to actually click on the value that I want to put in those parentheses. When I hit enter, I get 0 because the natural log of 1 is 0. Now you can either repeat the same thing for every column, but when you get a job, hopefully you'll have a job, you might end up analyzing thousands of data values. So in that case, you don't want to evaluate every single one. You want to process them all at once. So here's one way you can do that in Excel. You can turn your cursor over the bottom right corner until it turns into a plus. And then you can either drag it down or double click. Ta-da! This is a secret that one of my coworkers in the business world taught me, and not everybody knew that secret. So you can be very cool and save yourself a lot of time. Now notice that's sort of a ridiculous number of sig figs, especially considering that the original data in the data table had 3 sig figs for time. No, excuse me. It went to usually 2 decimals for the time, which sometimes was 3 sig figs and sometimes 2. And so let's say about 2 or 3 sig figs is going to be about right. So we're not turning in or publishing these graphs, so I don't have to be too meticulous. If you were actually publishing these graphs in a journal, then you would make sure every data value showed the exact precision of the instruments that you used, like that. Okay, so now I'm going to graph time, and I'm going to control click. Oops, excuse me, I'm going to drag these, and I'm going to do command click. So not control click, but command click. And that's going to let me highlight X and Y when they're not next to each other. And click on my graph. And there it is, ta-da! There's my natural log of a, and I see that it is a straight line, so that means it is first order. Now let's pretend this graph were not a straight line. Then I would have to check 1 over the concentration, or the reciprocal of the concentration, to see if it's second order. So I would say equals 1 over concentration. I can turn my cursor into the black plus, double click down. I can change the sig figs, or change the number of decimals reported, and then I can select X data, hold down the command key, select this data, and then make another graph, and I can see that that is not a straight line. So it's not zero order, it's not second order, it's first order, and then we're done. Hooray! And if we look at the question 3, letter C, use your graph to calculate the half-life. So the half-life is when the amount of material has been reduced by half. So I'm gonna start from 1, concentration of 1, and half of 1 is 0.5, so right around 7 minutes. Now, in this case, we were lucky because there's a 0.49 data value, but if there weren't a data value, we could use our graph. It's saying that, well, we started at 1, we can estimate down to 0.5, then go across and interpolate from the graph. So the half-life is approximately 7 minutes. Thanks for watching.